Hi Saints, this is Mr. Matthew Lim speaking. Today I'll be delivering the third DC circuit lecture. Let's look at the assessment objectives, show an understanding of the use of a potential divider circuit as a source of variable PD, explain the use of thermistor and light-dependent resistor in potential dividers to provide a potential difference which is dependent on temperature and illumination respectively. Let's look at the lecture notes. Okay, this is a potential divider. It actually consists of a battery source and two resistors in series, and these two resistors in series is in series with the battery source. All right, so you have seen this arrangement before. So I have two resistors here. So basically a potential divider divides the PD into two parts. So actually the 12 volt here, look at the 12 volt here, we are going to divide the 12 volt into two parts, that is into V1 and V2, all right? So how do we do that? First, I would like to introduce to you the potential divider formula. This is the potential divider formula. So if I want V1, I just take the fraction R1 divided by the total resistance in the circuit. So R1 divided by R1 plus R2 times E. So that will give me the PD across resistor R1. And here similarly, I can do that for R2. So the only difference is the numerator. Numerator this time is R2. I want the PD across R2, so I take R2 divided by the total resistance of the circuit. So this is the potential divider formula. So it simply helps you to find the fraction of PD um, across each resistor in the series circuit. So here, if you were to make a calculation, you'll be able to get the PDV1 as 7.2 and PD across V2, uh, PD across R2 as 4.8. Okay, let me write down. Okay, there is a shortcut in doing this. So if you were to look at the total resistance, you have 10 kilo ohm. So we call that the 10 units. So suppose I want to divide the PD 12 volt into two parts in the ratio of 4 is to 10. Then 4 part out of 10 of 12 is actually 4.8. 6 out of 10 of 12 is 7.2. So it is actually the ratio of the resistances. Okay, so PD across each resistor follows the ratio of the resistances. So as I go on, you will be able to pick up this concept. So let's look at example one. For example one, we have a potential divider which doesn't look that obvious. This time the power source is such that the highest point has a potential of 3 volt. So I call this point A, and point B is the lowest point. So the lowest point has a potential of minus 15 volt. So what is the potential at X? So to get the potential at X, what I'll do, I will find V1. V1, which is actually the PD across the resistor 300 kilo ohm. So I will use the potential divider formula. So I will have 300 divided by 300 plus 500. Okay, this is the fraction. Okay, fraction of the PD. PD is actually 18, which is 3 minus 15. So the PD between AB is 18, right? So if I calculate this, I should be able to get 6.75 volt, right? So V1 is 6.75 volt. So what about the potential X? Potential X is actually 6.75 volt below 3 volt. So I have 3 volt minus 6.75. Okay, so that will give me minus 3.75 volt. So potential at X is 3.75 volt. So this is one way of doing it. Another way of doing it is actually consider V2. Okay, let's look at this V2. V2. I can find the PD V2 using the potential divider formula. So I will do it again, but this time I find the PD across the second resistor. Okay, 300 plus 500 times 18. So 3 minus 15 is 18. That will give me a value which is 11.25 volt. Okay, 11.25 volt, right? So what is the potential at X? Potential at X is actually 11.25 volt above minus 15. So it's 11.25 volt above minus 15. So that will give me a value which is actually again minus 3.75 volt. So actually both ways I get back the same answer, right? So you may want to pause the video to appreciate the working, right? So this is the working for example 11. Right, shall we move on to example 12? Okay, example 12 is a work example. You have an EMF source E, and then you have two uh, two resistors. One is a variable one, so I call this V1. This is V2, V1 and V2, right? So um, there is a contact X that can be moved from the lowest point to the highest point. So the highest point is when PQ has a PD of, sorry, PQ has a resistance of 4 kilo ohm. Okay, so this is the highest point, highest X, highest point, highest point for X. So I bring P all the way uh, to the top. So that is why if I were to use a potential divider formula, um, I will have this fraction multiplied by the PD, which is 25, because PQ has a resistance of 4 kilo ohm. But if I were to bring this all the way down here, this is the lowest point, okay? So if I bring it to the lowest point, PQ will have zero resistance because basically P and Q are the same point, okay? All right, so in that case, PQ will have zero resistance here. So 0 divided by the total times 25, I get 0. So I'll be able to get a range. So the range for PQ is from 0 to 10, right? So that's the range, 0 to 10. All right, let's move on to example 3. Example 3, you were given a 20-volt battery with internal resistance of 2.5 kilo ohm. Is connected to a 50 kilo ohm device, voltmeter with an internal resistance of 120 kilo ohm, and an ammeter with negligible internal resistance are used to measure the PD across the device. So, and then you have current passing through the device as well. So 50 kilo ohm is that device. So this is the circuit that you ought to draw. Battery with internal resistance all enclosed in the dotted box. So the 50 kilo ohm in series with the ammeter and then in series with the battery. Voltmeter is always placed across the component, right? So ammeter is regarded as having negligible in resistance. So you have to take note of this one. So again, this is a potential divider because your EMF E is equal to V1 plus V2, right? So what is V1, V2? V1 is actually the PD across the parallel combination. This is a parallel combination, all right? It's a parallel combination. So this V1. V2 is the PD across the internal resistance V2. So we are going to apply the potential divider principle to get the value. So um, okay, in fact, before that, I think I have to calculate the resistance of this combination. So resistance of this combination is actually we take product divided by sum. So that is resistance across AB. So I call this AB. So resistance across AB is 50 times 120. Product divided by the sum. I hope you still remember from the previous lecture. So product divided by sum, that will give me a certain value, which is I think it's 35 point something, right? 35.3 kilo ohm, right? Okay, this 35.3 kilo ohm. So resistance across AB. So if I want the PD across AB, PD across AB, then I use the potential divider formula, 35.3 divided by the total resistance, 35.3 plus 2.5. Okay, so multiply by the PD, which is 20, right? So if I do that, I actually get a value which is 18.7. Okay, it is 18.7 volt. So PD across AB is 18.7 volt. But if I want the current through the 50 ohm resistor, this one, current, okay? So this resistor, the resist resistance of the device, I call it R1. If I want to calculate the current I1 going to R1, so I1 going through R1, so what I need to do is I will calculate like this, I1 equals to the PDVAB divided by um, the resistance R1. Okay, so that will be 18.7 divided by 5,000, 50,000. Okay, 50,000. That will give me 0.37 ampere, milliampere. Okay, so I'm going to minimize this and you can see how this question is solved. Okay, so the voltmeter reading is actually the PD across AB, right? So that is example 13. So let's move on to 14. Now 14 is actually a work example showing you a double potential divider. What do I mean by a double potential divider? If you look very carefully, there are actually two loops. So this is the first loop. Can you see this, the first loop? This is one potential divider, all right? This is the first potential divider. And there's a second potential divider here. They share the same battery. They share the same battery and then go through the second branch, okay? Back. So there are actually two branches. So as in all potential divider question, the PD um, is added up. Like for example, if I call this V1, suppose this V1, this V2, V1, V2, V2. Okay, so EMF E is equals to V1 plus V2. Okay, now there is a very important fact here that so far we have not considered. That is, uh, what is the value of R4 if the voltmeter reading is zero, no reading. So suppose I call this point A. Oh, this is so thick. So I want something which is not so thick. Okay, this one. Suppose I call this point A, this point B, right? So if there is no reading, it means that potential at A must be equal to potential at B, such that when they are equal, the potential difference is zero, all right? So it simply means that in such a situation, in such a situation, um, this is this is going to be V1, this is going to be V2. That means the ratio is the same. The ratio of V1, V2 for the upper branch and the lower branch are actually the same. So if I were to consider this is V1, V1 of the upper branch, and then this is V1 of the lower branch. Okay, so this part is the yellow part, V1 of the yellow part. This part is the V1 of the lower part. So if you were to look very carefully, you should be able to calculate R4 because you can cancel away E. You can cancel away E, right? So that will help you calculate R4. Okay, there's an alternative way. An alternative way is to consider current that goes through each branch. So suppose the current going through the upper branch is I1. Current through the lower branch is I2. Okay, so you will notice that the left ratio, this ratio is actually V2 divided by V2. Yeah, V2 divided by V2. So the numerator, this numerator, V2, this numerator is the V2 here. Okay, numerator is the V2 here. And the denominator, maybe I should use blue. Denominator, this V2 is actually this V2. Okay, this V2. So my V1, V2, okay, so this equal to V1. Uh, so this V2 divided by V2, this part is V1 divided by V1. If you look very carefully, the top part is actually, okay, the yellow part here, yellow part, okay, and the bottom part, um, I should use green. This one is this one, okay. All right, V1 divided by V1 is equals to V2 divided by V2 because of the ratio, the same ratio. Okay, so you should be able to obtain the value R4 equals to 4,000. Right, let's move on. Use a use of a thermistor in a potential divider. So what is a thermistor? A thermistor is a resistor whose resistance varies greatly with temperature. Okay, so you have to take note that it is a device where the resistance decreases with increasing temperature. It's the reverse. That means the higher the temperature, the lower the resistance, and the lower the temperature, the higher the resistance. And it's illustrated in example 15 because when the resistance is low, 800 is considered low. When the temperature is high, and when the resistance is 5,000, much more than 800, resistance is high. When it is cold, temperature is low. So it's the reverse. So determine the potential at W when the temperature is hot. So the focus here is when temperature is hot. So when temperature is hot, the resistance here is actually 800. Let me write down 800. Okay, 800 ohm. So to find the potential W, I will find the PD V1 first. Okay, this V1, V1, V2. So I will find V1 using the potential divider formula, 800 divided by 800 plus 1,700 multiply by the PD. The PD is actually 7 minus 2, right? 7 minus 2. The highest minus the lowest. So my V1 is, what is my V1? Um, my V1, if I calculate, I'll get 1.6, right? And then to get the potential X or W, potential at W is actually 1.6 volt above the lowest point or the lowest potential, which is 2. So it's 2 plus 1.6. I will get the potential at W. So this 3.6 volt. Okay, so that's the answer. Okay, 3.6 volt. So it's not that difficult, right? So let's look at the use of a light-dependent resistor in a potential divider. So what is an LDR? LDR is actually a device, a resistor, whose resistance um, decreases with increasing light intensity. Okay, so the higher the intensity, the lower the resistance, and vice versa. So in this case, when it is in the dark, the resistance is high. When it is in the light, the resistance is low, okay? Relatively to each other, you see 2 kilo ohm is low considered to compared with 6 kilo ohm, or rather 6 mega ohm. 6 mega ohm is much bigger than 2 kilo ohm. So we must focus at what the question want. Determine the potential at P when the LDR is in the light. So in the light means in this is the case in the light. So I will find the PD here. The PD here, I call it V1. Actually, it doesn't matter which one you call V1, which one you call V2. So I choose to call the top one V1. So I will calculate the PD, knowing that in the light, the resistance is 2 kilo ohm. So V1 is calculated using the potential divider formula 2.0 plus 3.0 and then multiply by the PD. PD is 18 minus 3. Okay, 18 minus 3. So if you make a calculation, you will get 6 volt, right? 6 volt. So what is the potential at P? Well, potential at P is actually 6 volt below 18. 6 volt below 18. Then you get 12, right? 6 volt below 18. So let's look at the solution. Yeah, 12 volt. So you may pause for a while to look at how this is done. Okay, we have reached the last example for today. This last example is slightly more complicated because you are given a current voltage graph for a diode. Okay, this is for the diode. All right, so be careful that this graph is for the diode. And again, this is a potential divider question where EMF is 1.5 volt, and then you have PD VR. Instead of V1, V2, now I VR, and then I have, oh, let me write properly, VR. That's the PD across the resistor, and this one is VD, diode. So I will write the equation EMF equals to VR plus VD, right? So this 1.5, and then you have VR plus VD, okay? So let's look at the question. So we want to see whether um, this circuit is suitable um, to determine the graph as shown. Okay, this is the task. Is it suitable to give you the graph as shown? So we will focus at two ends, two ends of the graph. One end is the lower end and another end is the upper end. So look at the upper end here. This is the upper end. So for the upper end, I will try to get the values here, the values. So you also try to read the values. Okay, let me let me draw it properly. I don't have a ruler. I can't use a ruler here. So you'll find that these values are actually 1.1 and 1.1 volt and 9.2 milliampere. Okay, that's the point shown by the arrow here. Okay, the arrow show the upper end. That's the upper end. So if the PD is 1.1 volt, so what is the PD across the resistor? So if I write this as 1.5, the EMF, this one is what I want to find. And then according to the graph, the PD is 1.1, right? So this is the 1.1. So it's a series circuit, but I already know the PD. Um, PD across the diode is 1.1, so VR is actually 0.4 volt. Okay, 0.4 volt. Now, is it possible to calculate the resistance of VR? Yes, resistance of VR, um, or in fact it's R, resistance of the resistor. So I've PdVR divided by the current, which is 0.4 divided by the current. Current is 9.2 milliampere, right? So that will give me a value of 43.5. So, so this resistance is reasonable, okay? So 43.5 is still within the range because the range was given to be between 0 and 100, okay? So 43.5 is within the range. So this is possible. The upper end can be achieved. Now, what about the lower end here? This is the lower end where current is 0. Now, this is where the trouble is because current um, in the, let me see, the current in the circuit. The current in the circuit is the EMF 1.5 divided by the total resistance uh, R plus R of diode. Okay, so um, we know that in order to get zero current, the denominator must be exceptionally high, uh, infinitely high. In fact, infinitely high to get zero current. And we know that this is not possible because the maximum value of R is 100. Okay, that's a maximum value of R. So the resistance of the diode um, is certainly not high. So as a result, the lower end is not achievable. Okay, so so that's it. To prove that this circuit is not suitable for determining um, the graph shown. So today, what we have done here is to learn how to apply the potential divider formula. So yeah, you just have to practice it. Practice until you know how to apply the potential divider formula. So that's the end of today's session. Thank you. Bye.